Hello, this is Dr. Strickland. In this video, we will investigate calculating the pH of a salt solution, part 1. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So when you do the analysis of a salt solution, it involves a lot of the same skills that we've been talking about recently. So the preliminary work is still the nomenclature and the classification and the analytical concentration, and then we'll know what calculations to do. So when you have a salt, you're going to have a cation and an anion. And so we're going to calculate the pH of a salt solution when the cation is the conjugate acid of a weak base and the anion is a conjugate base of a strong acid. So we're going to do this one here, trimethylammonium chloride. And so the nomenclature part looks like this. This is the trimethylammonium ion, and then the chloride ion. And so the analytical concentration is right here. All right. And now we need to know about classification. Now, this guy right here is a salt. You can tell because it's got a cation and an anion. But we need to take it apart and see what exactly the cation is and what exactly the anion is to know whether they will have impact on the pH of the solution. And with some salts, it's just the cation, and some it's just the anion, and some it's both, and some it's neither. So we're going to do two salts, one this time and one in the next video, one that focuses on the cation and one that focuses on the anion. So let me show you what I mean. So we've got our salt here. All right, the trimethylammonium chloride. And when you put a salt in water, to whatever extent it dissolves, it dissociates. Now, come back up here. Is this a soluble salt or a slightly soluble salt? And how do you know? Because it could be one or the other. All right, so now you need to know solubility rules. And remember that anything that has an anion that's a chloride, almost all of the chlorides are soluble. And so this is not one of the exceptions. So we're good. Because it's soluble, that means that when we put it in water, we're going to get 100% ionization. Okay, so that means we'll have this guy as the cation, and then this guy as the anion. Okay, so let's do a brief ice table here. Okay, the analytical concentration always goes in this spot. And when we first put everything together, there's none of this. We don't have any common ions from any other source. If we've got total ionization, then every bit of this is going to dissociate. Right? So when we reach equilibrium, there's none of this, but we do have some of these. So this is 0.200 molar, and so is this. Okay, so to determine whether we need to take one or the other of them on any further depends on what they are and what their separate classifications are. Because if you look at the chloride ion is the conjugate base of a strong acid. That makes this a very weak base, and it has no impact on the pH at all. Now, this guy here is the conjugate acid of an amine, and you know that all of the amines are weak bases. The conjugate acid of a weak base is a weak acid. And so if it's a weak acid, then it will dissociate further. So I'm just going to label it like that and say, hey, this is something we need to look at. And this is what we will take on. Okay, so now our planning the work looks very much like it did with any other weak acid. We've got the analytical concentration of our cation, and I'm going to put weak acid there just to remind you. And we got to go from there to the hydronium ion concentration at equilibrium, and from there to the pH. Okay. So our weak acid cation will dissociate when it reacts further with water. So I'm going to set up the ice table for this guy. All right, there's the cation, mixed up with water. Okay, so the first thing I want you to do is pause the video and write the products. Pause the video, write the products, and come on back. All right, welcome back. So the products, if this is an acid, it's going to lose a hydrogen cation and turn into its conjugate base. And it donates the hydrogen to the water, which is acting as the base. And because this is a weak acid, this is a double arrow. All right. Now, because it's a double arrow, that impacts how we set up the ice table. All right. So I want you to set up the ice table, put in what goes in all these different places. You know, the water doesn't count. And then come on back. All right, welcome back. So you know that the initial concentration of this cation is the same as the analytical concentration of the salt to begin with, right? It went from here to here, and now we're to here. And we know that at the very beginning, before any reaction happens between this cation and the water, there are none of these. But because this is the double arrow, it's only going to partly dissociate. It's not going to 100% dissociate like it did up here. Okay, so the equilibrium concentration of the cation will be this. And then its conjugate base will be that. And hydronium ion concentration will be that. All right, so this hydronium ion concentration, this is what we were talking about up here. Okay, so that's right there. And let's make this guy orange just to be complete. Okay, so where are we? Well, I think we need the equilibrium constant expression. Okay, so here's the equilibrium constant equation. I want you to write the equilibrium constant expression and then come on back. All right, welcome back. So it should look like this. That product times the concentration of this product divided by the concentration of this reactant. And if you look up this value, you would find that it's 1.59 times 10 to the minus 10. All right, so now we're ready to do some algebra. All right, so we've got our Ka value, 1.59 times 10 to the minus 10, and that's equilibrium concentrations of those two things from the right of the equation divided by the equilibrium concentration of the thing to the left of the arrows up here. And then the question, of course, is, can we do this? All right, so how are we gonna take that, test that? All right, so need to know the relationship between the analytical concentration of the cation and the Ka. Okay, so I want you to do that. Set that up and see, and then come on back. All right, welcome back. So what have we got? We've got 0.200 for the analytical concentration and 100 times the Ka value, which is 1.59 times 10 to the minus 10. So we're good because this side is going to be 1.59 times 10 to the minus 8. All right. Excuse me for that. So we're good. So we've got the analytical concentration times the Ka, and then we're going to take the square root. And I got 5.639 times 10 to the minus 6. Okay, so now we got to remember what X was. Well, it's the hydronium ion concentration. Now, before we take this any further, we should test that assumption. And we test the assumption using the percent dissociation. We want to know, is the percent dissociation less than 5%? Okay, so what do? Well, we've got to have X 5.639 times 10 to the minus 6 divided by the original concentration, what it came from, 0.200 times 100. And I got 0.00282%, which is well below 5%, so we're good, which means we can go ahead and calculate the pH from this. And so we'll finish this up. 5.24, and then we'll drop the guard digit from there, so 249. Is that what you got? Let's scoot this over just a smidge, so that's on the screen. So let's answer the question. Write me a sentence. Pause the video. Write a sentence. Come on back. All right, welcome back. I would say you can write the name of the solute out in words if you'd like. The 0.200 molar trimethyl ammonium chloride solution has hydronium ion concentration, and you can put the EQ for equilibrium down there if you like. 5.64 times 10 to the minus 6 molar, and pH of 5.249. All right, so that is the basic story on how you deal with a salt that has a cation that's acidic and an anion that has no impact. If you have any questions, please send them to me.